So lattice enthalpy is one of the enthalpy changes that cannot be determined directly. And in order to calculate then the lattice enthalpy of a compound, we have to construct enthalpy cycles involving other enthalpy changes that will allow us to calculate the lattice enthalpy of a compound. One of those enthalpy cycles is a Born-Haber cycle, which I cover in other videos. In this video, we're going to be looking at the other enthalpy cycle that can be used to determine the lattice enthalpy of a compound. And this particular enthalpy cycle involves two more enthalpy changes. And the first enthalpy change we'll look at is enthalpy change of solution. Now, enthalpy change of solution is when we take 1 mole of a solute, usually an ionic compound, and the ionic compound will dissolve in a solvent, which is usually water. So we're taking 1 mole of an ionic compound and we're dissolving it in water. Now, this process can either be endothermic or exothermic, and the reason for that is because this process involves both bond formation and bond breaking. I'm going to try and use this diagram to explain how or what is happening when we dissolve an ionic compound in water. So here we can see we have got the solid ionic compound, which in this case is sodium chloride. The ions are all very closely packed together. We've got strong ionic attractions occurring in all directions between the oppositely charged ions. Now, in order for that compound to dissolve in water, those strong ionic bonds have to break down. And when they break down, that allows the ions freely move in the water. So something must be causing those ionic bonds to break down, and it is in fact the water molecules themselves, because water molecules are polar molecules, meaning that one end of the water will be slightly negative and one end will be slightly positive. Now, there's obviously going to be attraction then between the negative end of the water molecule to the positive ions, which is represented here. So we've got this positive sodium ion that's being surrounded by water molecules, with the negative end of the water molecule being pointed towards the positive ion, because obviously opposite charges attract. And then here we've got the same thing happening, but you can see the water molecules are flipped over because it's the positive part of the water molecule this time that's attracted to the negative chloride ions. So if the attraction between the water molecules and the ions is strong enough, it will cause the ionic bonds to break in the actual compound, allowing the ions to become free to move. So we've clearly got two processes happening here. We have got new attractions being formed, so electrostatic attractions being formed, and when we're forming these new attractions, it's going to be an exothermic process, so it releases energy, and in the process we're obviously breaking down the solid ionic compound, so we're bond breaking so that the ions can become free to move within the water, which is obviously an endothermic process. Hence why the overall enthalpy change of solution can either be endothermic or exothermic. It will all depend on how much energy is released when forming these attractions and how much energy is taken in when breaking down the ionic bonds in the compound. So that's enthalpy change of solution. The second enthalpy change that will allow us to construct this cycle is hydration, so enthalpy change of hydration. And this is when we take ions that are in the gas state and we dissolve them in water to form 1 mole of aqueous ions. So each individual ion in an ionic compound will have its own hydration value, and I can represent this using chemical equations. So if I wanted to show the hydration of the sodium ion, according to the definition, we start with it in the gas state, we then add it to excess water, and I can show that by using AQ, and we're forming 1 mole of the ions that are now aqueous. So we go from ions that are gases, dissolve them in water to form 1 mole of ions that are aqueous. I can also show this with chloride ions. So I take chloride ions in the gas state, dissolve them in water to give me 1 mole of aqueous chloride ions. So that's what hydration is. We're taking gas ions, adding them to water to form 1 mole of aqueous ions. Now we can take those two enthalpy changes and we can use them to construct an enthalpy cycle that will allow us to determine the lattice enthalpy of a compound. Now, There are different ways that you can construct this cycle. I'm going to show the way that I prefer. Now, I prefer to put lattice enthalpy at the top of the cycle. So lattice enthalpy, if we remember, is when we take the ions in the gas state and they react together to form 1 mole of an ionic compound. Okay, so for me personally, I like to have lattice enthalpy of formation at the top of this enthalpy cycle. Now we need to involve hydration and solution. So solution, remember the definition, we're dissolving ionic compound to form aqueous ions. So we're going to go from the ionic compound and we're going to form ions, but this time they're aqueous. So this arrow here represents the chemical reaction that's taking place, and the chemical reaction that's taking place is the enthalpy change of solution. So I'm dissolving an ionic compound in water to form aqueous ions. And then the final part then is we can link the gas ions and the aqueous ions together by using hydration, because hydration, according to the definition, is taking ions in the gas state and dissolving them in water to form ions that are aqueous. So there is my preferred way of constructing this Hess cycle. You can also flip it over so that lattice enthalpy goes at the bottom, or you can have it so that hydration is on the top. You can even have it another way to have solution on the top. It doesn't matter. If you have a good understanding of the enthalpy changes and you know the definitions and you understand what's going on, you should be able to construct an enthalpy cycle without having to memorize. So whatever, pick which one you prefer, or just learn the definitions really well so that you can construct one from scratch. Let's apply this to an example. Let's apply this to sodium chloride. I'm going to use the enthalpy cycle that I prefer to use. So for sodium chloride, at the top of the cycle, it's going to be lattice enthalpy of formation. And according to the definition, that's when we take the ions in the gas state and we form 1 mole of the solid ionic compound. So there's the equation that represents the lattice enthalpy of sodium chloride. I then going to show the equation that shows the solution, enthalpy change of solution of sodium chloride. So we take the compound, we dissolve it in water to form aqueous ions. So there's the equation that represents solution. Now for hydration, the ions have their own individual hydration values. So I'm going to have to draw an arrow for each individual ion. So sodium will have its own hydration value. So there's the arrow that represents the hydration of sodium ions, and chloride ions will also have their own hydration value. So now I've constructed the enthalpy cycle, I can come up with an equation that's going to allow me to calculate lattice enthalpy. And according to Hess's law, I can calculate lattice enthalpy by indirectly by forming these aqueous ions and then forming or going to the sodium chloride ionic compound. And according to that, then I will take the hydration values, and from that I will minus the solution value. And the reason that I'm minusing it is because if you look at the enthalpy cycle, the arrow for solution is pointing downwards, and in order to calculate lattice enthalpy, I would have to do the reverse of that in order to get to the sodium chloride. So I'd have to go in the opposite direction, so I'd have to reverse the arrow, and that means I'd have to change the sign. So it actually becomes hydration minus solution. So that's how you use this enthalpy cycle to calculate the lattice enthalpy of a compound. Thanks for watching. For more chemistry tips and revision, hit subscribe, click on the like button, and check out my Instagram page using the link below.